In this video, we're going to take a look at geometric series. In particular, we're going to introduce the concept of a geometric series and discuss how to determine whether a given geometric series converges or diverges. A geometric series is a series that can be written in the form sum n equal 1 to infinity of a times r to the n minus 1 power, where a and r are just two real numbers and a is not 0. If we were to write out the first several terms of this series, starting with n equal 1, we would get the terms a times r squared, and a times r cubed. And then, of course, the series will be the sum of all terms of this form. Notice that the key property of a geometric series is that to go from one term to the next, we end up multiplying by the number r. So starting with the first term a, we can multiply by r to get the second term, a times r. We then multiply that by r to get the third term, ar squared. We multiply that by r to get the fourth term, a times r cubed, and so on. So here, the main aspect of a geometric series is that every term is the previous term in the series multiplied by the number r. When we have a geometric series, we call a the initial term, and again, that cannot be 0. And we call r the ratio. And this term makes sense because if we take any term in our series and divide it by the previous term, what we've just seen is that we will always obtain the number r. And so it'll be our constant ratio of one term divided by the previous term. Here are three very basic examples of geometric series. Our first one, we have the sum n equal 1 to infinity of 1/2 to the n minus 1. So here we can think of this with an initial term a of 1 and a ratio of 1/2. We have 1 times 1/2 to the n minus 1. So this will be a geometric series with these parameters. Our second series, we have the sum n equal 1 to infinity of -5 times -3/17 to the n minus first power. Here our initial term is -5, and our ratio is -3/17. And so both our initial term and ratio here are negative, and that is perfectly fine. And last but not least, we have the sum from n equal 1 to infinity of 2 times 5 to the n. We do need to be a little bit careful here, because the form of a geometric series requires the ratio r to be raised to the n minus first power. And here we have 5 to the n power. And so what we need to do first is to rewrite this term so that it has our form a times r to the n minus 1. In order to do this, what we can do is rewrite this as 2 times 5 to the n minus first power. So we're using properties of exponents to break off one of the 5s from the 5 to the n. And then, of course, 2 times 5 will be 10. And so we'll have 10 times 5 to the n minus first power. And now we have the form that we need to write down our geometric series parameters. We have our initial term a of 10 and our ratio r of 5. As we continue to discuss geometric series, it will be of the utmost importance that in the general term, a times r to the n minus 1, the ratio r is raised to the n minus first power. And so if it's raised to some other power, like in this case where we have 5 to the nth power, we need to first rewrite it so that we have an exponent of n minus 1 in that general term. Since geometric series are defined by two numbers, the initial value a and the ratio r, we're led to the following natural question. For which values of a and r does the geometric series n equal 1 to infinity of a times r to the n minus 1 converge, and for which values does it diverge? In a perfect world, we'd like to be able to answer this question in such a way that by simply looking at our geometric series and determining the values of a and r, we'll be able to easily determine whether the series converges or diverges. And it turns out that for geometric series, this is possible. In order to see how this is done, we're going to start by looking at the partial sum for our geometric series. So S sub k, the kth partial sum, will be the sum of the first k terms. So we'll have a plus AR plus AR squared. And our kth term will be a times r to the k minus first power, which we'll obtain by substituting k into the general term ar to the n minus 1. At this point, we actually have to break our thought process up into two cases depending on the value of r. The first case that we're going to consider is what happens when r is equal to 1, and this will be a very easy case to deal with. The more interesting case, well, what happens when r is not equal to 1? And so this will require a little bit of algebra and a little bit of calculus to determine what happens in this case. But first, we're going to deal with what happens when r is equal to 1. And so if r is equal to 1, we can rewrite our partial sum by replacing r with 1, and we simply get a plus a times r, which is just a times 1, or a, plus a times r squared, which is a times 1 squared, which is again a. And because 1 to any power will be 1, all of our terms, including our final one, a to the r k minus 1, will be a times 1, which is just equal to a. And so here what we're doing is we're adding the number a to itself k different times. So we see here we actually have k summands in this sum. And so if I add a number a to itself k times, we just get the product k times a. And so if I want to determine whether our geometric series converges or diverges, we simply want to take the limit as k goes to infinity of this particular partial sum. And so here we have the limit as k goes to infinity of s sub k. This will equal the limit as k goes to infinity of k times a, that product. And remember here that a is a non-zero number, but otherwise it's just a fixed number. It's just an unknown number. But as k goes to infinity, k times a will either go to positive or negative infinity, depending on whether a is positive or negative. If a is positive, this will go to positive infinity, and if a is negative, this will go to negative infinity. In either case, this sequence will diverge. It'll diverge to either positive or negative infinity. And so this tells us that in our first case, when r is equal to 1, the geometric series is going to diverge. So what we've done so far is we've answered the question that when r is equal to 1, regardless of the value of a, our geometric series will diverge. The more interesting case happens now, where we'll look at what happens when r is not equal to 1. So when r is not equal to 1, we're again going to consider our partial sum s sub k, which will be a plus ar squared, up to the term ar k minus 1, just like it was before. What we're going to now do is we're also going to consider the expression r times s sub k. So we're going to multiply this sum by the number r. When we do this, this amounts to multiplying each of the terms on the right side of our equation at the top of the screen by r. And so we obtain ar plus ar times r, which is ar squared, plus ar squared times r, which will be ar cubed, all the way up to our final term, which will be a times r to the k minus 1 times r, which will be a times r to the k. So effectively, all we've done by multiplying our sum by r is increase the exponent of r by 1 in each term. We're now going to subtract these two equations. On the left side, we simply have what we have. We have s sub k minus r s sub k. But on the right-hand side, we're going to get a lot of simplification. Notice, for example, that both of our equations have an ar term on the right-hand side. And so when we subtract the terms from the bottom equation from the terms in the top equation, the ar's are going to cancel. Likewise, both equations have an ar squared, and so when we subtract, those terms will cancel. In our bottom equation, the ar cubed term will cancel with the ar cubed term in the line above. And moving all the way to the end, we know that a times r to the k minus 1 will cancel to the a times r to the k minus 1 term in our bottom equation that is the second to last term. And so when we subtract everything, almost all of our terms cancel out. What's remaining is an a from the first equation. Everything else will cancel. And the second equation, the only term we have left is this a times r to the k, and we do need to remember that we're subtracting it here. And so when we subtract our equations, we're left with s sub k minus r times s sub k equals a minus a times r to the k. By doing this, this allows us to solve this equation for s sub k and therefore find a formula for our kth partial sum, and then we can take the limit of that formula to find determine whether a series converges or diverges. In order to solve for s sub k, we just need to do some algebra here. On the left side, we can factor out an s sub k, and we're left with 1 minus r. And on the right-hand side, we can actually factor out an a, and we'll be left with 1 minus r to the k. We can then divide both sides by 1 minus r, remembering here that r is not equal to 1, and so 1 minus r we know will not be 0. And so dividing by a non-zero number on both sides of an equation is always allowed. So we have s sub k equals a times 1 minus r to the k all over 1 minus r. And here is a very nice formula for our partial sum s sub k in terms of the numbers a and r. And so if we wanted the 10th partial sum, for example, of our geometric series, we would just let k be 10 on the right-hand side of this equation. However, the nice thing about this is that we can use this formula for the partial sum to determine when our geometric series converges and when it diverges by taking the limit of this as k goes to infinity. So we can compute the limit as k goes to infinity of our partial sum, s sub k. We use our formula that we just developed for s sub k. So we have the limit as k goes to infinity of a times 1 minus r to the k over 1 minus r. Notice that a and 1 minus r are actually constants in terms of k. A and r are the values that we get from our geometric series, and so when we're looking at a particular geometric series, these are fixed numbers. And so because they are constants, we can use limit laws to bring these out front in front of the limit. And so we get a over 1 minus r times the limit as k goes to infinity of 1 minus r to the k. And so we now have a relatively simple limit, 1 minus r to the k, as k goes to infinity to compute. At this point, we have to start considering what happens for particular values of r. For example, let's suppose for the moment that the absolute value of r is strictly less than 1. In other words, we have a value of r that is somewhere between -1 and +1, not including either of those endpoints. If that's the case, then the limit as k goes to infinity of r to the k is going to equal 0. And we can think through this logically by imagining r to be some number between positive and -1, and thinking about what happens when we take larger and larger powers of that number. As we take larger and larger powers, the total expression will get closer and closer to 0. And so this means that the limit as k goes to infinity of r to the k will equal 0. On the other hand, if the absolute value of r is greater than 1, in other words, if r is less than -1 or r is greater than 1, if either of those cases are taking place, then our limit as k goes to infinity of r to the k will not exist. This will be a divergent limit. Again, we can just kind of imagine what will happen if r is such a number. If r is a number bigger than 1 and we take larger and larger powers, those numbers will go off to positive infinity, and that sequence will diverge to infinity. And if r is a number less than -1, the same type of behavior applies, except every other term will be positive and every other term will be negative, and so we have just a divergent sequence. In any case, we can take these two cases and substitute them into the limit of our partial sums to obtain what will happen for various values of r. When absolute value of r is less than 1, we'll be able to compute the limit as k goes to infinity of 1 minus r to the k, and therefore find a convergent sequence of partial sums. And when the absolute value of r is greater than 1, we're going to see that this limit of the sequence of partial sums diverges. And this answers all of the questions we might have about the convergence or divergence of a geometric series. So we know the limit as k goes to infinity of s sub k is a over 1 minus r times the limit as k goes to infinity of 1 minus r to the k. When we have a value of r whose absolute value is less than 1, this is going to equal a times 1 minus r. And the limit of 1 minus r to the k will be 1 minus 0, since the absolute value of r less than 1 gives us a limit as k goes to infinity of r to the k equaling 0. And this, of course, will just be a times 1 minus r. And so in this case, we see that our geometric series will converge. And not only will it converge, but we actually know its sum. The sum of our series will be the number a, the initial value, over 1 minus the ratio r. And on the other hand, when the absolute value of r is greater than 1, we've seen that the limit as k goes to infinity of r to the k doesn't exist, and so the limit that we're trying to compute of s sub k will not exist, since it depends on that limit of r to the k. And therefore, in that case, we see that our geometric series will diverge. So this gives us a complete answer to the question posed earlier in the video for asking for which values of a and r a geometric series would converge and for which values it would diverge. Notice here that the value of a actually doesn't make any difference in what happens. The convergence or divergence of a geometric series is determined solely on the value of the ratio r. As a quick summary, here's everything that we need to know about the convergence or divergence for a geometric series with initial term a and ratio r. When the absolute value of the ratio r is less than 1, the geometric series will always converge. And in this case, the sum is always going to be the number a over the 1 minus r. So the initial value over 1 minus the ratio. When the absolute value of the ratio is greater than or equal to 1, the geometric series will always diverge. Notice that we've really only shown this second case when the absolute value of r was greater than 1. We did look at the r equal 1 case separately at the very beginning, and the r equal -1 case is very similar. We can look at that very particular case, see that the series diverges, and therefore we can throw that into the divergent case as well. It is worth noting that this result here only applies to geometric series. And so if we have other series that are not geometric, if they're not able to be written in this form, a times r to the n minus 1, then nothing here applies to that particular series. Here are 3 geometric series that we looked at earlier in this video, and we identified the initial term a and the ratio r. We can now apply what we've seen to easily determine whether these series converge or diverge, and to determine the sum for those that converge. Our first geometric series has a ratio of 1/2, and so this is a number which has an absolute value less than 1, and so this will converge. We can then find the sum by using the formula a over 1 minus r with the values that we are given. So here a is going to be 1 and r is 1/2. And so we get 1 over 1 minus 1/2. And when we simplify, we see that that is going to be equal to 2. And so our series n equal 1 to infinity of 1/2 to the n minus 1 is a convergent geometric series with sum equal to 2. Our second series has a ratio of -3/17, and the absolute value of that is 3/17, which is definitely less than 1. And so again, we get a convergent geometric series. The sum here, again, is given by the formula a over 1 minus r. A is -5, and r is -3/17. So we get -5 over 1 minus -3/17. And after all the arithmetic is performed correctly, we get a sum of -17/4. And so here we have a convergent geometric series with a sum of -17/4. Our third geometric series has a ratio of r equal to 5. The ratio there is bigger than 1. It's greater than or equal to 1. And so this tells us that our geometric series will diverge. And because it diverges, there is no sum. We know this will have an infinite, this sum will get larger and larger the more terms we include. And so there's no sum to find in this case.